Okay, so we're here to present RIDL Rogue and Fly data load. Let's check if this works. This project was a collaboration with Fusek at the Vrije Universiteit Amsterdam. So it's Stephan, Schaik, Alyssa Milburn, Sebastian Osterlund, Pietro Frigo, Kaveh Razavi, Herbert Bos, Cristiano Gifrida, and Georgi Maestradze from CISPA. So you might have read about this in news. We got a lot of media attention. This was also called MDS attacks by Intel. So there were a bunch of speculative execution attacks that were presented in May this year. Well, there were a bunch of news articles, and yeah, in total there's 4 attacks, I think, that were presented on the same date. So let's start with a short background on speculative execution attacks. So basically, speculative execution is one of these optimizations in modern CPUs so that you can hide, for example, memory latency. And the thing is, these optimizations should be invisible to the user. And typically what you have is this optimization where, suppose you have a variable called imp here, for example, user input, that has to be read from memory. Typically, it takes a long time to load this from memory, right? So the CPU will at some point just try to speculate the value of this condition here instead of wait until it's read from memory and then correct it at a later stage. So you might, the processor might execute the wrong branch and then later kind of turn it back and actually execute the right path. The problem with this is that since this wrong path is executed, an attacker might leak this value that has been read in the speculative branch using a cache attack and be able to leak sensitive information in this way. So now Stephan will give you a short, or well, not short, actually a long introduction on cache attacks and all the background information required for these kinds of attacks. Go.
So let's first talk a bit about cache attacks. So just to give you a little bit of background. So what used to be the case is that in the past we just had CPU registers and well, main memory and disk storage. And what we found out over the years, like 20, 30 years, is that, well, the CPU is progressing at a very fast rate. So it's gaining clock speeds very quickly, while main memory and disk storage are lagging behind. And one of the solutions to this is basically to put smaller memory in between the CPU registers and main memory, which is basically smaller, but also at the same time faster. So at the top you have like the CPU registers, which are basically very small and fast, and then you have like level 1 cache, which is a bit bigger, but also still fast enough. And then once you go down lower, you get like large main memory, like nowadays it's like 16 gigabytes, but it's also much slower to access. And what we, there's some terminology for cache attacks to understand. So if you access data and it's in the cache, then we call it a cache hit. And if it happens to be not in the cache, then we basically, it has to come from main memory, maybe from disk storage, and we call it a cache miss. To give you an understanding of cache attacks, I will give you one example of a cache attack that is called flush and reload, and this is a very typical example of a cache attack, and it consists of 3 stages. So the first one is the flush stage, the second one is the victim stage, and the third one is a reload stage. And what happens here is that on the side you also see the probe array, and the probe array is basically an array of data that the attacker can access. So what happens first is the flush stage. And the idea behind the flush stage is, well, remember, if it's in the cache, it's called a cache hit and it's fast to access. If it's not in the cache, it's slow. And what we're trying to do with the flush stage here is basically we execute an instruction on every entry in the probe array as follows: to flush every entry such that it is no longer in the cache. And now if we want to access any of these entries from their array, it's slow to access. Now the victim runs some code. In this case, it runs tries to use the secret as an index for some array. And what happens is that the victim will load an entry into somewhere into the cache. And now the attacker will try to infer which entry has actually been loaded. And the way it does this is basically by reloading every entry to measure the time it takes. So the first access is slow, comes from DRAM. Second access is slow, comes from DRAM. Third access is fast because it's cached. And now the attacker knows something about the secret that the victim was using. So previous attacks you might have seen over the past few years are Meltdown, Spectre, and Foreshadow. And for this talk, to make it simple enough for you to understand, we'll just focus a bit more on the meltdown part. So to apply this example to meltdown, we now have 4 stages, and you basically see 2 stages are already very similar, like flush and reload, and we still have this nice probe array. So how does meltdown work in a nutshell? So the first step is that meltdown has a victim, which in this case is the kernel, that accesses some data in the kernel. And what happens here is basically that data will end up being cached, preferably in the level 1D cache. And then the attacker proceeds as normal. It just flushes the entire array. And then the meltdown part happens. And the meltdown part is basically a transaction, which means that the CPU will speculatively execute something. And in this case, the code is shown here. And the first thing it will do, I also have to look a bit myself. So the first thing it will do is basically it will try to access that kernel address that the victim also used. And of course, that shouldn't be able to happen in user space, but we're doing it speculatively. And what happens here is basically the attacker will now actually read some data from that kernel address speculatively. And then it will just access the probe array to leak that data. And how does it do that? Well, it uses the secret byte that it has read from the kernel as an index for the probe array. So now something in the probe array gets cached, and the attacker can now simply proceed with the reload step, where it basically starts timing every entry again. So the first one is slow because it's from DRAM, the second one is slow because it's from DRAM, and the third one is fast because it has been cached. And what does this mean for the attacker? Well, the attacker now knows that the third entry has been cached, which means byte 2 was the one that it read from the kernel address. So what are the mitigations against these things? So there are different ones. So like especially depending on the kind of attack we're talking about. So kernel page table isolation is the one against meltdown, but there's also array index masking against Spectre and some masking against foreshadow. And for this talk, we're simply going to focus on the meltdown part. So what's the problem? So what it used to be like basically before 2017, 2018, every process was laid out as follows. So like you have an address space, and in the address space, you have like your user space, which contains like the executable, the data it uses, whatever, as well as the kernel. So what you would have is like every time you would jump into the kernel to have it do something, and then it would basically jump back to user space all in the same address space. The problem is like if you have seen meltdown just now, then you realize that you can just leak kernel data by accessing these virtual addresses. So how do we solve that? Well, we basically introduced 2 address spaces, one which contains user space and kernel space into the same address space, and this one is the one used by the kernel. And then we have another address space with just the user space, but barely anything of the kernel space mapped in, such that when we try to refer to the kernel, there's no address that actually points to something in the kernel. So let's say we now have a system with all the mitigations in place. So here we have a machine that we have at a university, and this machine has an Intel Core i7 7800X, which is a Skylake X workstation CPU. And if you look back then at the time, what kind of features it has and like the mitigations it has installed, you see it basically has all the mitigations against meltdown, the different Spectre variants, and L1TF, which is foreshadow. And we're basically like showing you here that, well, this system is fully up to date, has all the mitigations in place. Okay. So as you can see, it has all the mitigations. And the question is, of course, well, we're an attacker, can we still do something on such a system where like you have the mitigations against meltdown, you have mitigations against Spectre and foreshadow? What can we actually do as an attacker? Well, so on this system, you have a file called @c2shadow, which is very common for Unix systems. And @c2shadow is a file you cannot access as a normal user. You have to be root to be able to access it. And for instance, on the second line, what you see is like we just print the first line, and what you see here is the root account has a password hash. And on the third line, we're basically running our RIDL program, which tries to leak that password hash as a non-root user here. And you can actually see that it is actually leaking the same bytes as the first entry. But of course, as you can see here, it takes a while. It actually takes around 24 hours, and this was our initial attempt to do this without any kind of optimization. But you can actually see that you can just leak this entry using the RIDL attack. So meet rogue and fly data load, or RIDL, and this is basically a new class of speculative execution attacks that knows no boundaries. Well, to show you that it knows no boundaries, we're first going to talk about privilege levels, and they're just basically a social construct. What we've shown here is that, well, if you have you have a CPU with two hyperthreads, as was the case with Intel, and still is the case nowadays, we can just leak between these hyperthreads. But the question is, of course, on a modern system, you also have different security domains. Like you have the kernel, you have the hypervisor, you have different VMs. You might even have something called SGX, which provides security enclaves. And the question is, can we still leak across these from different security domains? And the answer turns out, yes, we can. So we can leak from the kernel, we can leak across VMs, and we can leak from the hypervisor, and even from these SGX enclaves. Basically, we leak across all the security domains. And then another question we have is, like, okay, nice, you can leak from VMs, SGX, I don't care, I care more about my browser. What about my browser security? So can we actually leak from the browser? And it actually turns out we can, as we will also show later on in this talk, because we actually managed to reproduce RIDL in Mozilla Firefox, and this shows that there's no need for any special instructions to do these kind of attacks. So, conclusion for the first part here is, well, we leak across security domains, and we can even leak from the browser. Another social construct is basically memory addresses, so there's also a social construct. So to come back to the previous attack, so we have Meltdown, Spectre, and Foreshadow, and what we noticed with the previous attacks is that they mostly rely on leaking from addresses speculatively. And what this means for mitigations is quite simple. Well, you can solve this by just masking or isolating these addresses. If you just hide the addresses, there's nothing to leak, right? Well, so that's what they exactly thought. So like if you have Spectre, you can access out-of-bound addresses. If you have Meltdown, you leak kernel data from virtual addresses. If you have Foreshadow, you basically even leak from the physical addresses. And so if you look at the mitigations, what they did is, well, with Spectre, they just masked their array index to limit their address range such that you cannot do these out-of-bound leaks. With Meltdown, you unmap the kernel from user space. And with Foreshadow, you make sure that your physical addresses are invalid so that you cannot leak from these physical addresses. Great. So in a nutshell, previous attacks, they exploit addressing, and they basically mitigate this by isolating and masking addresses. So RIDL, on the other hand, it does not depend on addressing. What this basically means is that it bypasses all address-based security checks, and this makes RIDL a bit hard to mitigate. So a bit of a side question, but now that we've shown you, like, okay, we have this system where we can execute a RIDL attack program and actually leak the password hash from etc. Shadow, for instance. One of the first questions you might ask as well, in addition to the security domains, is like, what CPUs are actually affected by RIDL? So what we did is, like, we bought Intel and AMD CPUs from almost every generation since 2008, which means we also had to buy some of them secondhand. And we basically sent all the invoices to our Professor Herbert Boss, who gladly paid for this. And we built an IKEA rack, as you can see here. And this basically has all the motherboards that we bought, installed with the CPUs, nice cable hazard. And what we found is basically that RIDL works on all the mainstream Intel CPUs since 2008. So here's a list of the CPUs we actually tested. And at some point we looked at, so this was in September when we found RIDL. And at some point, Intel started announcing a new generation, so the 9th generation of Intel CPUs. And they had a nice table, and they basically announced the generation called Coffee Lake Refresh. And what they promised us is, well, this generation of CPUs has in-silicon mitigation against Meltdown and Foreshadow, which means you don't need the software-based mitigations anymore. Sounds very interesting to us. So we decided, like, okay, let's buy the Intel Core i9 9900K. And send another invoice to a professor. So basically, we submitted the paper to Oakland S&P in San Francisco. And the day after we submitted the paper, we actually got the box. Okay, we can still do something with it. So we actually checked, and what we found is that, well, nice that you have these nice in-silicon mitigations, but of course, they seem to also do something with the addresses, so RIDL still works. So we can add it to the top of the list, so it also works on the Intel Core i9 9900K. And then we basically started looking at different CPU vendors as well. So the next easy target would be AMD. And well, we tried to reproduce it on AMD, actually on 3 different AMD processors. And what we found out is that, well, AMD seems not to be affected, which is also in line with their media coverage. So these are the 3 AMD systems we tested on, and we couldn't find anything. So we think it's perfectly safe in this case. But great. So RIDL Insight, because it runs great on Intel. But the question is, of course, well, you're not leaking from any of these addresses. So you're not leaking from the cache as shown by, as is the case from Meltdown. So where are we actually leaking from? So it turns out CPUs are quite complex. So here's a part of the diagram. And well, so the previous attacks, they had it kind of easy. They just leak from caches. You have level 2 cache, you have level 1D cache. And for us researchers, well, we already have a lot of material on like manuals, papers, whatever you name it. And caches are basically well documented and well understood. But the problem is that RIDL does not really leak from these caches. So where else can we leak from? So it turns out there are like other internal CPU buffers. And in this case, the parts we highlight here is like the line fill buffers, the stall buffers, and the load ports. And there's also more. So there's also uncached memory. And basically, what we found is that RIDL actually leaks from various internal CPU buffers. So what this shows is that RIDL is really a class of speculative execution attacks. And to Intel, it has been named as microarchitectural data sampling, also known as MDS. So that's why you usually see both RIDL and MDS being mentioned in the news articles. So do not make it very complex here, because there are many different sources that we can leak from. We basically focus on one particular instance for the remainder of this talk, which are the line fill buffers. So where would you find information about these line fill buffers? So there's not much research being done on these things. Well, you can start by looking at the Intel manual. So Intel has a nice manual of a few thousand pages that you can read through. We tried to look a bit through this to find any mention of this. And what we found is that there are some references, like 1 or 2 sentences here and there about line fill buffers, but no further explanation. So where would you start? You just have this manual. It doesn't mention anything really. Okay, so what we decided is, well, you know what? If you have a great idea of how to optimize your processor, you will probably patent it. So that's what we decided to do. We decided to actually read the patents instead. So these are the patents we basically printed and read. And, well, I survived, so I'm here to talk to you about these now. And I can tell you a bit more about how what kind of clever tricks they pulled off to implement these CPU buffers. So what are these line fill buffers exactly? So again, so you have the diagram here. And what line fill buffers are, they're basically central buffers. So to show this is like we have the caches here together with the execution units where the instructions are being ran. And right in the middle there, you have the line fill buffers sitting right between the caches and the execution units, and they're there basically to improve your memory throughput. So line fill buffers, they have multiple roles. So they're there to allow asynchronous memory requests. I will talk to you about that a bit more. They allow you to do load squashing. Basically, if you have loads to the same cache line or stores to the same cache line, so start combining them. So you basically reduce the number of memory requests, and they're also there for uncached memory. If you're a CPU designer, you're basically thinking in terms of like, I want better performance. So what do I do if I get a cache miss? Well, the naive way to do this is, well, you just send out a memory request. You wait until it completes, like until your memory comes back, which takes probably 300 cycles. And then what this does is like, well, you do nothing. You block everything else. You block your other loads and stores. You're not making any progress. So what did these people think of? Well, you know what? We can just introduce a buffer called the line fill buffer, and we keep track of the addresses there. So what we do is like, okay, you send out a memory request, you allocate a line fill buffer entry, and then you store the address in the line fill buffer entry. In the meanwhile, you just serve other loads, other stores, other instructions while you wait for the memory to basically tell you like, oh, here's your data. And at some point, you actually have the memory controller telling you like, okay, your data is here. you can now basically deallocate the line fill buffer entry and you complete the load restore. And where it goes wrong is really like the allocate LFB entry part. What happens here is that the LFB entry may still contain data from the previous load. So it's basically the same as a use after free problem. And this is exactly what RIDL exploits. So what you see in the Intel CPUs is that these buffers basically have stale data from previous loads and stores that you can leak data from. So we carried out a bunch of experiments. And what we found is that basically RIDL leaks from these line fill buffers. And with that, now that I've talked to you a bit about the low-level details and on which CPUs it works, across which security domains you can pull out a RIDL attack, we can now talk a bit more about the high-level details, and I will let Sebastian do this part for you.
Okay, thank you very much, Stephan, for all the background. So let's have a look on how we can actually exploit this leaking of data. So we had a bunch of experiments showing that, okay, we can leak data, but now we want to do some actual exploitation with this. So, of course, we've shown that we can leak so-called in-flight data from these CPU buffers. So let's come up with an idea and get some sensitive information in flight. So typically, how to get some sensitive information in flight is to do a so-called confused deputy attack, where you have some privileged process pulling in data, and then you try to leak it somehow. So the observation we made is that the password utility on Unix reads the etc shadow file content. So use the password utility to change your password. And of course, it has to read the hashes from the etc shadow to be able to do this, to check that your actual password is correct and so on. So another thing that we can do on standard Linux setup is to use the task set utility to control the affinity of the process, to say on which core or which hardware thread a certain process should run. So what we're going to do is simply try to leak, well, the contents of the etc shadow when we invoke the password utility from another co-located hyperthread with our RIDL attacker program. Well, this turns out to be not so easy, so I'll discuss that in a bit. But at least the first challenge is done. We can get some sensitive data in flight. So the second part is actually how to leak the data. So now I'll show you how the actual RIDL attacker program looks like. So the one leaking from the line fill buffers. So it looks very similar to the previous attacks, like Meltdown and other cache attack things that Stephan was talking about. So basically you have the first, the flush part, where it walks through the buffer, flushes all these entries. Then we come to the RIDL part. So if you recall from the Meltdown one, you did a dereference of a kernel pointer. Well, this is not possible anymore since KPTI. You won't leak any data. But suppose you just leak from a null pointer here. So for the record, we're inside a transaction, so we suppress any faults. We don't get a seg fault here. Basically, we're inside a so-called TSX transaction. So basically, we dereference a null pointer. The thing is, since the optimizations here will try to use some in-flight data, so it will actually, it won't, the address null is not available, so it will read some in-flight data from the line fill buffer, so previous data, stale data from the line fill buffer. Then we use this data that we leak from that as an offset into this array. So suppose the stale value in the line fill buffer was 3, and then we dereference that offset into the array. So we offset 3 into the array, and later we start measuring these things. So we walk through our probe array one by one. The first one we see, okay, the access is slow, so it's not cached. This one is not slow, it's not cached. It's slow. And this one is fast, so it turns out this is cached, and that's exactly the value that we leaked here in the previous steps, because we access this one and then the value is cached. So we now have a primitive to leak data that we're actually not supposed to see. But the problem is that this approach is like drinking from a fire hose. You just get whatever in-flight data that's available. So we have to do some other things to actually make this a realistic attack. So the third challenge is to actually filter the data, do some post-processing. So we had two ideas. So first one is to do some kind of synchronization so that you time the leaking with exact time when the desired data is in flight. Well, that turned out to be really hard because we can't modify the binary, so we can't insert some kind of synchronization primitive. So we simply have to do some post-processing. Nice thing about this attack with the password utility is that we can repeat it infinitely. So we can just repeat the attack, do a lot of measurements, and try to stitch the observed values together. So how does this work in practice? So recall, we want to leak from etc shadow. The first line of this file is usually for the root entry. So it starts with these characters, root colon. So here you see a screenshot of the etc shadow file on my computer, I think. So as you can see, it starts with root. So this is always known. The file starts with this. And then, of course, well, what we can do is you can use some kind of prefix matching. Because since we already know a part of the data we want to leak. So what we do is if we see a match with our previous measurements, we assume that the following byte after that is correct. If it's not a match, we just discard the measurement. So we can actually discard all these garbage measurements. So have a look at this. So suppose, okay, we start with knowing that this is the beginning root colon. Then we do a measurement and leak this. So for example, you might leak something from the web browser accidentally, but this is not what we want to leak. It's not conforming to our previous measurements, so we'll just discard this. Now suppose we have this next measurement, which contains root at the beginning. We assume that this is a correct measurement and assume that the byte following our known string is a valid one. So now our new string is root colon s. Then we do another measurement. Well, this is something that's not relevant. But now we get something that's, again, matches with our previous measurements. And we go on and on, byte by byte, until we get a whole desired string. So now we have a way of kind of filtering this data to stitch multiple measurements together. So what we now can do is, well, as we already showed in one of these animations here, that we can leak the root password hash from unprivileged user on a normal Linux system. So let's extend this attack a bit to the cloud. Of course, the cloud is hyped nowadays, so we want to do some cloud attacks. Well, suppose we have a victim VM in the cloud that we want to attack. So we want to do a similar attack like this that we had like locally. We obtain attacker VM, for example, on Amazon, and we make sure that it's co-located. So a lot of cloud vendors share hybrid threads between different VMs. So the actual line fill buffer is shared between these things. So using a RIDL attack, you can steal information from the line fill buffers. Of course, like this victim VM, usually on a server, you're running an SSH server, right? And, well, one observation is that the SSH server, reads the etc shadow file when it tries to authenticate the user. So how do we get the etc shadow in flight? Well, we launch an SSH client from our attacker VM, repeatedly open SSH connections to our victim, which in turn, once you try to authenticate, will load the etc shadow contents into the line fill buffers. And, well, the contents are now in flight, and we just do our standard attack that I just showed you. We run the RIDL attack on our attacker VM to leak the contents from the line fill buffer and stitch the measurements together. So we can actually leak the etc shadow file from a co-located VM in the cloud. So we also have a few more examples of attacks that we did in the paper. So one thing we can do is leak some internal CPU data, which I won't go into detail now, so we can leak page tables. We also have an arbitrary kernel read, so we can read arbitrary kernel data, and we can also do this attack from the browser. So a quick note on the arbitrary kernel leak. First of all, what you can do is combine Spectre, so one of these previous attacks, with RIDL. They're so-called Spectre gadgets, which are available all over the place in the kernel and in user programs that if you can execute, then you can, in speculative execution, you can leak data that you're actually not supposed to read. So using these gadgets, we can actually force the kernel to read some stuff into the line fill buffer, and then we just leak it with our RIDL attack that we already had. So to give you a concrete example, the copy from user function in the kernel can access arbitrary user supplied pointer. So if you repeatedly call the set R limit system call with valid user pointer, you train the branch predictor to actually predict the branch to be valid and read this pointer that you supply it. After training, you can supply it a kernel pointer, and speculative execution will read this pointer, pull it into the line fill buffer, and then we can leak it using our RIDL attack. So let's have a look at how this works. So we have the set rlimit system call here. We call it a bunch of times from user space with the valid user pointer, so it just behaves normally. It calls copy from user, goes here, just copies it from user, and you do this a few times to train the branch predictor. Then at some point when you're confident you have trained the branch predictor, you give it an invalid address or a kernel address. Well, now it goes, starts executing. Set rlimit, copy from user, goes here. Then at some point this, in reality this is false, but since the speculative execution doesn't know the actual value of this, it will just predict that the branch is true and will execute this speculatively and load this data into the line fill buffer. And now we can actually leak it, right, with the same program that we already showed you. So, okay, we can do an attack on cloud VMs. We can leak arbitrary kernel data. So let's do some even more stuff. The browser, of course. So one of the problems is portability. So the example I showed you relies on Intel TSX or hardware transactions. This is not available in common browsers, so we have to figure out some alternative for that. CL flush to flush this probe array is also not available, so we have to figure out something for that. So this program that I showed you is not really realistic from the browser. But fortunately for us, there's some alternatives. So if you don't have CL flush, we can do some other cache attacks. So we can do evict and reload, which has been shown in previous work to work from the browser. So we can actually do a cache attack from the browser. Well, no TSX is also an issue, but we've been able to actually suppress the error using demand paging, which is an operating system feature where if you get a page fault, you basically, the memory that you're using is not always mapped, and it maps it on demand as you access it. So you can actually suppress invalid memory accesses in this way. So what does the program look like now if you don't have TSX, don't have CL flush? Well, first of all, you have something like evict. So we don't show the whole evict cache attack here, but basically you can use any of these things to evict the cache. Then what we do is speculatively read as a secret. So we have allocated, we do mmap and get a new page, which has not been mapped in yet because it's demand paged. So you will get a page fault here, but it's not noticeable from user space because the operating system caches it and maps in the actual page. Then we use, now we're in speculative execution, right? So we have this value that we leaked here. So it will dereference invalid memory in speculative execution. There won't be any memory there, so it will use values from the line fill buffers, for example. And then later on, it will kind of access this probe array that we had. And in a similar way, we can leak it here with this for loop, right? So we dereference it here, and then we can leak it. So the nice thing about this code is that it's kind of portable, generic, and we can generate something very similar like this from WebAssembly. So we can do it in the browser. So here we have an example of this running in the SpiderMonkey JavaScript engine. So this is not the GUI browser, but just the JavaScript engine, just because it's easier. You get this clearer signal if you just run the JavaScript engine. But as you can see, we have a victim program that I think prints hello world, right? Or something, hello meets, yeah, so some string, and then we can leak this from JavaScript. So let's talk a bit about existing mitigations for speculative execution-based attacks. So basically there's three mechanisms, right? So the first one is to inhibit the trigger, which is to stop speculation, add fences, and red boolean, and these kind of work to stop speculation, but you have to manually insert these fences all over the code, and it also can hurt performance a lot. The second one is to hide the secret. So this is something like KPTI that Stephan discussed, and array index masking and flushing the caches. So you actually kind of hide the data so that these attacks can't access it. And then there's the thing to disrupt timing channels. So for example, all modern web browsers have added some noise to their timers so that you can do accurate cache attacks. Well, there's a paper by Google came out a few months ago that shows that actually you can still do these things even with this noise added to the timers. And all of these other mitigations kind of fail because they assume addressing. So these previous mitigations for these types of attacks don't work for RIDL. So after we disclosed this in May, well, Intel was already working on some mitigations, right? So they also released it on the same day. They released their microcode patches. So one of the first things that you can do is well, you can leak from the same thread. So this is, for example, for the arbitrary kernel read that we have. So the mitigation provided by Intel is that they patch the ver.w instruction such that it flushes some of these buffers that are affected. So for example, it flushes the line fill buffers. So on every context switch to the kernel, you do a ver.w so that it flushes the buffer so that the user cannot leak this content anymore using the RIDL attack. Of course, you need the microcode update for this, and it's not always available. Suppose you're a client in like a VM. You don't know if the host actually has this microcode patch applied. So they also provided some assembly snippets that you can insert that should basically flush these buffers. And it looks like this. Who knows what it does, but I think it seems to work, but yeah. Then for the other variant, like the cross-thread one where we have two hyperthreads, it's a bit harder because you leak data that's in flight and there's no way to kind of synchronize the ver.w thing. So the ver.w thing only works if you leak from the same thread. So Intel came up with some complex scheduling policies to kind of prevent this. Here's a diagram they have in their white paper. As you can see, it's horribly complex. But basically what it says is that two threads should always be in the same security domain. And you have to synchronize until you go, when you go to a different security domain. So, well, of course, no one is implementing these scheduling strategies because the performance it will take a huge performance hit. So our suggestion, like to actually mitigate, is to just disable hyperthreading. Then you will fix the cross-thread problem. Of course, looking at this diagram that Stephan made, well, the data from reading all the patents, he was able to make this nice diagram. You can see there's a bunch of buffers going on here. Like it's not only the line fill buffer, but it's horribly complex. And these mitigations that Intel gave us are, of course, another so-called spot mitigation, which just fixes this one issue and doesn't fix the fundamental issue where you have shared resources that other people can actually access. So one question you might have is the attack actually realistic? Stephan showed you this animation where it takes 24 hours to leak the etc shadow. So 24 hours, no one cares, right? Luckily, we have some master students. So we had a master student, Jonas, doing a term project on optimizing our attack. So I would actually like to show you a live demo. Hope it works. So let's see. I'll try to SSH into our server. Yep, okay. So first of all, we have a victim that I'll start up here. And basically what this victim does is what we already said. What? Oh, it's not on the screen. Shit. Let's see. I have to move this. Let's see. Yeah, it should work. Okay, let's see. Okay, thanks. Let's see. Let me increase the font size a bit because it's super hard to see, I think. Is this visible or should I increase? Yeah, let's increase it a bit more. So basically, we have a victim here running the password utility in a loop with task set so that it runs it on a certain hardware thread and just keeps doing this all the time. So it actually doesn't need a password or anything, just do password-s and your username and pipe the output dev null. We don't care about the output at all, just gives you a warning. Then the attacker, let's see, we're here. I have a nice demo script. Hope it works. So first of all, well, you can see we execute cat of etc shadow. Is it visible? Should I increase the font size a bit more? That's good. Okay. So we do cat etc shadow. We see, okay, permission denied. We can't access it. So now, of course, we do sudo to actually see the contents of this. So here you see the actual string that's in the etc shadow file. And then I do sudo k to actually kill my sudo session so I'm not root anymore. So I shouldn't be able to access the etc shadow file. And now we start this leaking the attack. Hope it works. Yeah. As you can see, it goes fairly fast. I think, yeah, one by one. Okay, so here we actually leaked the root password hash in 16 seconds, which is kind of amazing, right? It's so we had this master student working on this for, I think, a month or so, and like hyper optimized our proof of concept. So thanks to Jonas for this nice demo. So this kind of shows that this attack is. I don't know what this. Oh yeah, this is just the backup in case the demo wouldn't work. Always have a backup, right? But luckily it worked, right? So amazing. First time I've had a live demo that worked. So. So what we have shown here, like, okay, we can do this in 16 seconds, or we've also been, sometimes we managed to do it in under 10 seconds, right? So that's really fast to leak the password hash. So kind of the take-home message here is that we need to fix these at the fundamental level before people start abusing these in the wild. So if someone just adds resources, tries to optimize these things, I'm pretty sure you can also do this fast from the web browser at some point if someone just puts in the effort. So then, a bit about the disclosure process. So we discovered this in September 12th. We reported it to Intel. I think we discovered it the day before, and immediately the day after we realized, okay, this is serious. Let's report this to Intel. In between, we got an answer back from Intel that yes, submit to our bug bounty program. We started writing a paper and submitted the paper on November 1st. Then Intel contacted us in December saying, oh, there's also some other people who found this in the same time frame as you, basically. So these are the people who also found these kind of issues. So Georgie wanted to collaborate on a paper, so we added him as a collaborator on the paper. And, well, then the paper got accepted in December, and for a while it was kind of nice and quiet. And then disclosure was set for May 14th, and just a few days before disclosure, Intel comes say, hey, wait, there's also more finders, by the way. And so basically we have a word cloud here of all the different finders. So I think the first one to find this issue is George. He found it in, I think, June of 2018. We found it in September, and the rest found it either like in late autumn or January, February, April. But yeah, as you can see, there's a bunch of people working on this stuff. It's a crowded area. So we also have a website, MDS Attacks, that we collaborate with some other groups that also found these similar issues. So we have a unified landing page where people can find our papers and read more about the kind of what happened with these attacks and what you need to do to prevent them. Stephan also wrote a nice tool that you can download and run on your computer to see how vulnerable you are to RIDL and other attacks such as Spectre, Meltdown, and all kinds of things. And I think we continue to try to update this tool to add new attacks as they become available. So, conclusion, we thought Spectre Meltdown was just one mistake. Well, I think we were wrong. We have presented RIDL, a new class of speculative execution attacks. We can leak from many more buffers than the caches, not only caches, but all of these other internal CPU buffers. And most importantly, RIDL does not rely on addressing, so it's very hard to mitigate it properly, especially like across security domains and in the web browser. And of course, you can follow us on Twitter and go to the website for more information. And with that, I would like to thank everyone here in the audience. Thank you. So, any questions?
Thank you both for the awesome presentation. Do we have any questions from the crowd?
Hello. You mentioned before the optimizations that your fellow researcher did. Can you explain a bit? Is that data analysis or like was the concept itself improved?
So basically it's kind of hyper optimizing the assembly, like which kind of instructions you use to leak, and then also optimizing the cache attack. So for example, if you want to just leak the etc shadow one, you know that only certain characters are in there, so you don't have to loop over all possible entries in the buffer, right? So there's a bunch of these things. So I don't know, I think we will have a write-up on these things later in November.
Are there any other questions? We shall move to the Slido questions then.
Yep.
The first one is, why would you advance the match buffer 1 byte at a time and not just grab the full buffer or the next X byte?
Okay, so that one is, so I understand why this question is asked. It's a very good question. So the problem is that you're doing this in a transaction or speculative execution window, and you only have a limited amount of instructions you can actually execute. And on top of that, you also only have a limited number of dedicated specific execution units you can use. So at most, we were able to leak 3 bytes at a time. And what happens is if you try to do this, it becomes even slower. So if you want to gain an optimum, it's usually somewhere like 1 byte or 2 bytes where you start matching this. Anything more is like, well, doesn't work or is super slow to do.
Thank you. Whoever asked the question, you could get your prize behind. Thanks. Do you have a question? Sorry? No. Okay. Another question on Slido. What artifacts, if any, would this technique leave on the system?
Well, there are some things you can find if you do these attacks, because technically you're flushing the cache a lot. And there are performance counters that basically tell you like how many times did you get a cache miss versus a cache hit cache miss versus a cache hit, for instance. And you would see this going up a bit. The problem is that I would guess this relates mostly to anomaly detection. And I would personally advise to focus more on the preventive side of matters, where you basically try to prevent these kind of attacks. And another issue is that if you try to do this on the cloud, you will just see that you will get a lot of cache misses anyway because of the kinds of workloads that clouds generally run there. I think performance counters are probably the biggest one where you would easily be able to detect these kind of attacks.
Yeah, but the thing is, so the thing is, it's not 100% foolproof. Like intrusion detection, you can always circumvent it by either doing the attack slower or masking it in some other way. So, yep.
Thank you. And the last question is, can this be leveraged for enumeration of a system? How does it compare to traditional enumeration?
So, do you know the concept? What kind of enumeration? Is there anyone who knows?
So I would guess that probably detecting what kind of system you're on. And in that case, well, you can, for instance, you can detect easily if it's Intel or AMD. And there's also so there's some behavior that you can notice with RIDL that would allow you to tell something about the CPU, but which specific one is probably pretty hard. So for Intel versus AMD that you can do, because on AMD it doesn't work the same way, or it doesn't work at all basically. And then you're just left with Intel, and then on Intel you even have the low end generation Atoms, where you basically cannot do RIDL because they don't really do that much speculative execution at all. So you don't see the same behavior. But other than that, it's not going to help you in a very basically pinning down which CPU you're actually running on in this case.
Any other questions?
Thank you. You did mention that you released a tool. Is that on the website so that people can use it?
It's all on the website. It's open source. You can download it. It runs on Mac, Linux, Windows. Yeah.
Okay, and all of these slides can be downloaded on the conference website, cyberweek.ae/materials. And with that, let's thank them again for this wonderful presentation.
Thank you.